Welcome to our presentation for assignment 5 of the mechanical sessional course code ME29002. Today we will be presenting our project on the railway ladder system. This project was carried out by the following group members: Yayavaram Vivekaditya, Pranav Jai Ganesh, Singidi Abhinay, and Vignesh. Let us discuss about the problem statement. The first objective of this project is to design and synthesize a deployable four-bar ladder mechanism that can smoothly extend and retract between the train coach and platforms of different heights. The mechanism must maintain proper kinematic performance and ensure reliable obstruction-free motion. And the second objective is to create a 3D model and motion simulation of the ladder system to evaluate its deployment behavior, structural stability, and overall feasibility. This helps verify whether the mechanism operates safely and is suitable for practical passengers use. Platform heights differ widely across railway stations, which often makes boarding difficult and unsafe for passengers. A compact deployable ladder can help bridge this gap by providing stable and reliable access between the coach and the platform. Using a four-bar linkage offers a simple, predictable, and efficient solution for this purpose. By designing and stimulating this mechanism, we can evaluate its movement, stability, and practical feasibility for real railway applications. Let us discuss now the way of approach what we have done. We began by making practical assumptions regarding the distance between the platform and the train, as well as the overall dimensions required for the staircase. Based on these assumptions, we defined the open and closed configurations of the ladder system. After establishing these boundary positions, we use graphical synthesis techniques to determine the appropriate link proportions for a four-bar mechanism. This was followed by detailed modeling and motion simulation in SolidWorks to validate the feasibility and performance of our design.
Grashof criteria. To ensure the mechanism's motion was kinematically possible, we apply the Grashof criterion for a four-link chain. The criterion requires that the sum of the shortest and longest links must be less than or equal to the sum of the remaining two. In our case, the shortest link was measured to be 120 mm and the longest 259.81 mm. The other two links summed to be 390 mm, thus satisfying the condition and resulting in a crank rocker mechanism where the shortest link is grounded adjacent to the frame. Synthesis. Stair dimensions. For synthesizing the staircase itself, each tread was designed with dimensions of 300 mm by 800 mm and a thickness of 20 mm, thus ensuring comfortable step size and proper structural accommodation. Kinematic analysis. We then performed a complete kinematic analysis of the mechanism, deriving expressions for displacement, velocity, and acceleration to understand the motion characteristics throughout deployment and retraction. Let's start with the displacement analysis. Using the vector closed loop complex number method to solve this, we get the displacement analysis equations as we know the location of all the points. For velocity analysis equations, we need to differentiate the displacement analysis equations. We get two equations, and if we solve them, we get the velocity analysis of each points, theta 1 dot and theta 2 dot. For the acceleration analysis equations, we need to differentiate the velocity analysis equations. We get two equations, and if we solve them, we get the acceleration analysis of each points, theta 1 double dot, theta 2 double dot.
I will now show you the simulation part of our project, which has been carried out in SolidWorks. SolidWorks is a powerful 3D CAD software that allows engineers to model, simulate, and visualize complex mechanical systems. Let me start by showing the simulation. Here, we have used a 4R mechanism for the project. I will now remove the train model first for a better visibility. Now, the 4R mechanism can be seen clearly and also the crank. Here, the red plate represents the ground link, which is fixed. This is a smaller link. This is the rocker. The remaining link is the coupler, We can label the mechanism as O2, A, B, O4. Each component was designed individually in SolidWorks. Let me show you the different components. This component is crank. Here are the dimensions of it. Length 120 mm, height 20 mm, thickness 20 mm. This component is coupler and its dimensions follow the values we determined during the synthesis stage. For a better distinction between the frame and the steps, we intentionally made the ground frame larger than the step size. We designed two types of step connecting links, long link and the short link. Let us see those in the mechanism part. Here, this is the short link and this is the long link because the short link is adjacent between two steps and the long link is adjacent between three steps. In this mechanism, the rocker has two fixed pivot points, so it oscillates within a defined range. When it reaches its extreme position, the railway steps stop moving, allowing passengers to board and alight safely. The crank is motor driven, providing uniform and controlled motion. We have chosen a step size of 80 cm, which we found to be comfortable and safe for all the passengers. To make it more real, extra outer parts were added around the crank. A key safety feature including is the fillet on the step edges, which reduces injury risk if someone stumbles or hit their toe. Now, let me show you the simulation part with the motor connected to the crank. As you can see, the motion becomes smooth and uniform due to the motor input. This is the final simulated mechanism.
Initial configuration. In the initial setup, the ladder is fully folded and not in use. At this point, the crank sits at about 165 degrees, which is our starting position. As the mechanism begins to move, we rotate the crank forward to around 19.2 degrees. This rotation is what drives the entire linkage and eventually brings the ladder to its fully open position. Dead configuration. When the system reaches the open configuration, something interesting happens. The links O2A and AB lines up almost perfectly, making them look like one continuous bar. This creates what we call a dead center position, and it represents the extreme point of motion where the ladder is completely deployed. Problems we came across. During the design phase of our model, we encountered a significant issue. Our first approximation, which used a right angle triangular layout, caused the mechanism to pass through a dead center position where the threads partially overlapped each other. This overlap posed a safety hazard as it created a potential tripping point for the users. Solution. To address this problem, we refined the mechanism geometry, adjusting pivot positions and link dimensions so that no overlap occurred at any point of the motion. This refinement ensured a smooth and safe transition between the configurations. Ideas for improvement. Finally, we identified several potential improvements for the future development of the model. These include integrating proximity sensors to automatically detect platform height and adjust the ladder, designing an alternative mechanism that can transform into an inclined plane for wheelchair accessibility, incorporating an interlocking safety system to ensure the ladder can only be deployed when the train is stationary, adding LED step lighting for better visibility and indicator lights to show the operational status of the ladder. Thank you for your time and attention. We hope you enjoyed the presentation. Thank you.